Okay, we can dive right into header analysis. This is going to hurt. You probably need to watch this multiple times. I'm going to do my best to not make any mistakes. So the first header that we can start with is our Ethernet header. This is going to be, thinking layer 1 and 2, dealing with MAC addresses on the OSI model. And as you can see here, we have our Ethernet frame denoted here for saying that this is a Ethernet header. All of these gray lines here, these are all going to be screenshots from Wireshark, are denoting different headers that you can have. So this is a header, this is a header. You have your IPv6 header, which we'll cover later, your UDP header, and then the bytes of the actual payload of the data that's coming over with the packet. So right now we're just on Ethernet header, which is just this one gray line here. Now, this is always going to be the first 14 bytes of the Ethernet frame. So if this is our whole frame here, it's going to take up the first 14 bytes. We'll have your MAC addresses and the next Ethernet type followed by the data and checksums. Now, if this is the first time you're seeing a header kind of broken out for what parts are allocated to what bytes, half the battle is actually reading the chart. So we're also going to be including on each slide a chart notation for what the values are associated to, and then mapping them out to whatever sample I've pulled from Wireshark. So it'll make more sense just as we go through these, just kind of keep an open mind. Watch it once, don't take any notes, and then watch it again and take some notes. So starting with the Ethernet header, the first 6 bytes are designated for the MAC address. That should make sense because 6 times 8 gives us our 48-bit MAC address that we've been talking about, our physical address. So if we start here, we will have the first 6 denoted as our destination MAC address. Wireshark allows you to, quote unquote cheat. It's a tool. It's going to take your hexadecimal notation and provide you over here with the easy to read format of it. And we can see here that the destination MAC address is 98597A580843, which is exactly what we allocated here for denoting based on the cheat sheet that we have for what's telling us is in an Ethernet header is being described here. So then the cheat sheet says the next 6 bytes are denoted for source MAC address, which will run from F4 all the way to E6, which we have. So that's the destination, or the source MAC address. Sorry, I'm already making mistakes. The source MAC address of the computer that it's coming from. And then the last most important thing to remember for the Ethernet header is the Ethernet type. So it's saying it's taking up 2 bytes. So we have 86DD. That means it's going to be an IPv6 packet coming next for what's going to encapsulate the Ethernet header. So since it's denoting IPv6 is going to come next, you'll see that the next header is actually also denoted here as IPv6. If you had the value of 0800 in these 2 bytes, that means you would have an IPv4 packet coming next to encapsulate this Ethernet header. If you had 0806, that means you would have an ARP packet coming. And just a couple of quick references that I'll make going through this. We tip before you sip at a restaurant. So to remember your Ethernet header, if you get confused as to which MAC address is the source or destination, T stands for target MAC. So tip comes before SIP for your source MAC address. So it's always target MAC address for where the packet's going from the next 6 bytes going to the source MAC address where the frame came from. So that is your Ethernet header. Now we can move into our ARP header. ARP we've talked about IP to MAC, we've covered this in previous modules. We've talked about ARP cache poisoning, making malicious modifications to the ARP table. We've talked about man-in-the-middle attacks, where someone can get in between your packets and act as the middleman and start relaying packets to however they choose to route them. Now let's dive into the ARP header. So the ARP header is going to come after the Ethernet header. So you have to remember, we just did our 6 bytes for our target MAC address, so our destination MAC address. Then the next 6 bytes take up the source MAC address. And then you see here our 0806. If we were to go back a slide, that's saying that the next packet to come along is an ARP packet. 0800 was for IP version 4, 0806 is for ARP, and 86 delta delta was for IP version 6. So we have 0806, which makes sense because we are looking at, in Wireshark, a ARP packet. So that comes before this header. So that means the actual ARP header starts at the next allocated bytes, and I've tried to highlight, if you can tell, it's a little bit more gray where the frame is, or where the header is going to start. So it's actually going to start here at the hardware type. And it says, again, half the battle is reading the chart. If you've never read headers before for the cheat sheet, it breaks it up into bytes. So this, if there was a line here, this would be the value of 1 byte. This would be the value of another byte. Protocol type is saying it takes up 2 bytes. This would be 1 byte here, another byte. This takes up 2 bytes. Server hardware address, it blends into 2 lines. That means this is 1 byte, 2 bytes, 3, 4, and it goes into the next line, 5, 6. So your sender hardware address, your MAC address, is taking up 6 bytes, which again, 6 times 8 is 48, so you know it's going to be 6 bytes. Your sender protocol address is taking up another 2 bytes, 4 bytes, and your target hardware address, 1, 2, 3, 4, 5, 6 bytes for that, and then your target protocol address is saying it takes up 4 bytes. So if you can extend these lines and kind of draw them down to separate reading this, again, that's half the battle. But we'll work through these and hopefully it makes sense for where they're splitting it and how the charts are supposed to be read. So the ARP header starts here at 0001. So we can fill in our hardware type, taking up the first 2 bytes of 0001. I like to just draw boxes around where each thing is broken up. We can see hardware type 0001 means Ethernet is our hardware type. The next section, it says it's protocol type, taking up 2 bytes. So that will be 0800. That value is going to mean IP version 4. The hardware address length is taking up 1 byte, so the next 1 byte is 06. Hardware size right there, 6. Protocol address length taking up another byte, 04. 4 is the value denoted there. Opcode taking up 2 bytes, so we have the next 2 bytes of 0002, which is a reply. And then we have our 6 bytes for our sender hardware address. So 1, 2, 3, 4, 5, 6. So the sender MAC address is D8 all the way through 94, which is D8 through 94. Sender protocol address, 4 bytes long, so the next 4 bytes. That is our source IP address, so C0, 8A, 01, 9D, which converts from hexadecimal. Remember from the previous slide, you should be able to spot out C0, 8, or A8 as 192.168, and then the rest of the IP address, 019 delta, converts to 1.157, 9 delta being 157 over here. Then you have your target MAC address taking up the next 6 bytes. So that's going to run 98 through 1, 2, 3, 4. We'll go back 1, 2, 3, 4, 5, 6, 98 through 43. And our target IP address taking up the last 4 bytes. C08A 192.168.1.43 in hex converts to 67 in decimal. So that was a lot of information to cover in there, but hopefully it will make sense as we keep going through different headers and reading the chart. All right, we have the next header up, the Ipv4 header. As you can see, we had our Ethernet header taking up 6 bytes, and then 0800 at the end of the Ethernet header, telling us that we have an Ipv4 header as the next segment. So that means the Ipv4 header is coming next. And if you can see where it's a little grayed, that means it's going to start at this byte value of hex 45. Now, if we read the chart, again, it's a bit complicated if this is the first time you're seeing it. It actually is saying the version is the first 4 bits denoted here. The header length is the next 4 bits. So this whole thing is actually 1 byte. The type of service is taking up another byte, and the total length is taking up 2 bytes. So there's actually 2 bytes in here. So this whole top thing is representing 1, 2, 3, 4 bytes. That's kind of complicated. I'm doing my best to explain it. Let's go through the packet. So we have 4. 4 we're going to square off on its own because it's taking up the first 4 bits here. 0100. Remember, if we do 8421, that means the decimal value is 4. So the version is 4 in hex. So IP version 4. The next 4 bits is going to the 5. So that those 4 bits are going to sit there at the header length. As you can see, the header length is 5 in hex, but if we want to get to 20 bytes, 5 times 4 gives us 20 bytes. So you have to do some math here to multiply the value of 5 times 4 bits to give you the total header length, which is 20 bytes. The type of service that takes up the next byte value, so we have 00. The total length is taking up the next 2 bytes, so we're going to have 0028 as broken out here as the next 2 bytes. The identification is taking up 2 bytes, so 4E, EB. The flags that are set, we have no flag set, as you can see here, the value of 00, so this is taking up 1 byte. The fragment offset is also 0, so this is taking up 0. The time to live value is the next byte taken up for F7. We talked about time to live before. So if we have our time to live, that is how long the packet has left to traverse through the network before it becomes expired, because we don't want packets just endlessly going from hot point to hot point, router to router infinitely. So they set a max time to live for the max number of routers or hot points you can traverse to. So we add in hex here F7, which equals the value of 247, which means the original time to live value must have been 255. There are default time to live values that you can have, 255 being one of them. You can also have the default value of 80 in hex, which equals 128. You can also have the default value of 40 in hex, which is 64 in decimal. These numbers should be familiar to you. And if you look at this packet, if you have F7 and your time to live is 247, if you know the default value based on the operating system that this was working under, so I know that this is 255 was the original TTL, you can actually calculate how many packets this has traversed to by just subtracting 247 from what you know the upper end value is to get you your 8 hops. This packet has taken 8 hops. That's probably additional information that goes beyond the scope, but TTLs, you should be familiar with what they are and some of the default values. And if you had a default value that converted out to 62 in decimal, you would know that this packet went 2 hops. The next byte is designated for protocol. So the next byte is 06. Put this over here. 0x06 means we are using TCP. 0x11 in hex is 17. So this is also decimal 17, which means we're using UDP. I would ingrain that, this is just 6 in decimal, that if you see in this spot here, 06, that means the next packet to come is TCP, the next header. Right there, you can see TCP. But if this were 11 in hex, that would be decimal 17. So this would not be TCP, it would be user datagram protocol for UDP. So keep that in mind. The next section we have is 2 bytes for the header checksum, 6B17, and then the source address, 18.165.53.61, 4 bytes for that. And then the next destination address, 192.168.167. Again, we see our C08A to tell us that's 192.168.1.43 in hex converts to 67 in decimal. So then the rest is options and padding. So from here to the end, you have a bunch of options and padding. So if we take our eraser here, kind of just clean this up a bit, what I want you to start realizing is the values that really aren't going to change. Like this guy right here is always going to be at this location. So I can kind of work backwards in my cheat sheet. If I know I'm at this field, I can skip 2 bytes for this value here. And then I know that these next 4 bytes and these next 4 bytes are my IP addresses that I'm looking for. And it's source and then destination. So you can kind of skip around. The other very useful thing to realize is 99% of the time, your IPv4 header, you're going to be looking for this 4500. It's always going to be usually version 4 with the length of default value of 20 bytes long, and then type of service always being left as usually 00. So you can kind of start skipping around when you start looking at hexadecimal notation for PCAP and header analysis to try and work backwards to kind of spot, oh, I know that's the start of an IP address. This means I'm using TCP 4500. That's the start of my Ipv4 header. And hopefully you can kind of start to shortcut this and start filling in some values and then either work forwards or backwards to get the information that you need. But that is our Ipv4 header. Okay, moving into Ipv6 header. This one's a little bit easier to digest than version 4. So we always look for the end of the Ethernet header. So now this value denoted is 86DD. That means we're going into Ipv6. So now I know the next header for Ipv6 is going to start right after my Ethernet header. So it's going to start at this value here for 60 as the first byte. Reading our chart, we see that this is the first 4 bits. This is the second 4 bits. This entire block here is for the first byte. So if I break out the first byte in half, I have 6 over here and 0 for my traffic. So 6 means I'm using Ipv6, traffic class, a value of 00. Next, we have the next 3 bytes denoted for our flow label, which is all zeroed out. So 1, 2, 3, 0, 0, 0, 0, 0, 0 for our flow label. The next 2 bytes are for payload length. So if we have 2 bytes, we have 0, 0, 2, 5. 2, 5 converted in hexadecimal gives us the decimal value of 37 for payload length. Then we have the next header taking up 1 byte, and we see that it is 11. Remember, we covered in the last slide, this is TCP, 11, which is 17 in decimal, is UDP. So since I can see a 06 or an 11 in hexadecimal, I know that I am at my next header to come in, and it's at 11. So now instead of TCP, I'm seeing user datagram protocol for UDP denoted as the next header that's going to encapsulate my Ipv6 header. Hop limit is going to take up the next byte. So we are at 40 there. 40 in hexadecimal converts to 65. So again, we also discussed TTLs or hop limits. One of the common values that we discussed was the upper limit of 64. So this packet is fresh out the gate with no value less than 64. So this is the first, it's going out the door. Then we have our source address taking up the next 16 bytes. 16 times 8 will give you 128-bit IP address. This is where we've sounded, like a broken record player where we're saying 32-bit Ipv4 address, that gives us 4 bytes, 128-bit Ipv6 address to give us 16 bytes. So the source address and destination address are both going to take up 16 bytes. Take a look at the Ipv6 nomenclature that they use for breaking out. It's shorthanded here for some of them with the double colons representing zeros, but if you count out the next 16 bytes, I do this shorthand because 8 and 8 is 16, so I know that these 8 here, I have 2 here, which means the remaining 6, if I kind of split it right here to take the other half of the line, that's where my IP address is going to start and finish for a full 16 bytes. So it starts at 26 right here, and it ends at E0, and D7 was right before it. So that is that right there. Delete that so you can see it a little bit easier. D7, E0 is the end. Again, 8 and 8 are split by this separation line. So 8 and then 6 and 2, I can figure out pretty quickly where my source address is going to start for the 16 bytes. Then the destination address is going to take up another 16 bytes. So you can apply the same math. It's going to start, I'll pick a different color. Start at the 26, 8, 10, and 2. I know it's ending at the same spot for 200A. 200A is where it ended. 2607 is where it started. So if we're not crying yet, then I'm not teaching the module correctly. Definitely a lot of information that's coming in here. We have to learn how to read these cheat sheets for our headers for the values that they're given. We have to understand where bits and bytes are allocated. We have to go find them in hexadecimal. We're converting hexadecimal to binary to decimal values to get IP addresses. We're throwing a lot of concepts that we've built on top of other modules. Just hang in there. That's all I can say. This one is going to be a module that hurts. All right, now we have our ICMP header. We just covered types and codes for ICMP types and code values that you can have based on what the message is going to say, whether it's destination network unreachable, host unreachable, port unreachable, echo request, echo reply, etc. Those were our type codes that we covered in the previous module. Now we can fill in our ICMP header and kind of see those concepts layered on into what we're seeing in the PCAP. So starting with the first byte, we have 0, 8. We're going to find where this starts. So we had our Ethernet. We see the Ethernet, the end of the Ethernet header told us 0800, which means we're going into an IP version 4 protocol. The start of the IP version 4 protocol, I can see this 4500, and it has the default length of 20 bytes. So I could count out 8, 16, 17, 18, 19, and 20 if I wanted to. And you can see where it kind of starts to get a little bit more gray as I've highlighted the ICMP header. That's where it ends. So if in blue we stick with our Ethernet header, that would be all of this. In pink, we would do our IP version 4 header to cover all of those bytes. And then in green, our ICMP header would cover all of the rest of the bytes seen here. Actually, that's not correct. It would cover the length for the extended header, and then whatever the variable length is for the actual payload of the raw data coming over for 32 bytes would be the end of it. Okay, so where were we? We found where we started our ICMP header. The first byte is denoted for 08. That's our type. Here are our type and code values for what the overall message is going to be. So a type 8, we go over to 8 is 8 in decimal. This is going to be an echo request packet for a ping. So we have an echo ping request. If we had so 0x08 is a ping request. If we had 0x00, that would be a ping reply, because the type and code value that we would have would give us an echo reply. So there's our type and code values right here. 08, and the next byte is 00. So we have a 08 for the type, which is going to tell us echo request. The next 2 bytes are for the checksum, as it's 16 bits. So 4A 9 alpha, or 95 is our checksum. Apparently that means correct. And then the extended header and data payload, really don't need to worry about this. The major points are being able to find out where your header starts based on the other information that we've learned, saying IC 0800, so I know the next header is IP version 4. I know usually 99% of the time my IP version 4 header starts with this 4500 and goes for 20 bytes, and then it's going to have the ICMP header come next, so I know that this is the starting place for my header, and I'm mostly concerned about the first 2 bytes here for my type and code message to tell me what kind of ICMP message is going to be displayed. The rest of it, if you want to memorize that, great, but review of ICMP, this was our critical protocol for IP, providing error messages, flow control, first hop gateway redirection, etc. It's more simple of a header, ICMP. All right, let's do our TCP and UDP headers next. So as you can see, we had our Ethernet header. We had the value of 0800 telling us we're going to IP version 4, 20 bytes long. This one's a lot easier to see where the 20 bytes ends here. And we have our 06 value there. Again, 11 being UDP, 06 being TCP. So the next header that's coming in is a TCP header. If we break out our cheat sheet here, we can figure out what bytes are denoted for what values. We have the first 2 bytes as our source port. So we have 01 BB. And that, if we break that out, just cheating in Wireshark, 01 BB converts to the, you do your 8421 for your binary, and in decimal, that would give you 443. So that is our HTTPS protocol that we are using. So a challenge question would be, is this the server sending the packet or the client sending the packet? Well, we know that the server is always going to have the main port protocol in use, and if this is the source port number in our value here and not our destination, this means that the packet is coming from the server, because the server will always have the lower port value and the client will have a random high port assigned. If we continue on, we have the next 2 bytes designated for the destination port number. That is CED4. Cheating in Wireshark, we see that as 52,948. So this packet has a source port of 443 and a destination port of a random high port. Looking at the frame of looking at the packet number 7 here for the actual one that we're looking at, this is the source IP and this is the destination IP, meaning that the 44.228.58.8 is the server IP and the 192.168.1.213 is the client. If this were reversed and the source port was the random high port, you would know that this packet is coming from the client because the server always has the lower port number. Anyways, a tangent, but this is where building onto the concepts that we've learned in previous mods really starts to come together, and I'm just trying to highlight the good information that's coming out. So 01BB, CED4, sequence number, the next 4 bytes, 1, 2, 3, 4. I'm not going to write that in, but it was 76 through C3. The acknowledgement number is the next 4 bytes. So we have those 4 bytes in there. The major thing that I want to highlight for the TCP header is your source port, destination port, being able to identify if this is the client or server packet that we're on. And the next thing is the flags. Flags, as we've talked about, are very important for TCP. We talked about our SYNs, our ACKs, SYNACKs, FIN, push, urge. We have a bunch of flags we can use with TCP to tell us what's going on with the packet. As we can see here, the flag value that is set is 0x010. We need to break this out because this chart is also confusing. If we erase some of this, this is saying that the first 4 bits here are allocated for the data offset, and then you have 010 allocated for your flags here. So you have 4 bits here, 4 bits here, and 4 bits here. So you have 12 bits to work with for your flags. So let's break this out. We have a flag value of 0x010, which gives us an acknowledgement flag. If you can see, it says 3 bits and then 9 bits. So if we break all of these out as 4 bits, 4 bits, and 4 bits, counting backwards, 9 bits would go this 4 bits plus this 4 bits to give us 8, and then 1 of the 4 bits broken out. So if we assume, just for simple separation of where the bits are falling, the 9 bits cover this much area, and then the next 3 bits are set for your reserve bits. So it's breaking up 3 denotions of spaces it can take up for 1.5 bytes, or 9 bits and then 3 bits to give you 12. Hopefully that math makes sense. And then your data offset was the other 4 bits that would make up the rest of that byte. Now that I've thoroughly confused you, their flag values do have different values associated with them, which we will cover when we go into the next slide for TCP flags in more depth. But that is the most important thing to realize when you're looking at the TCP header. To realize where your flags are going to be picked up, it's always going to be on the row on the end. So 010 is right here. 010. If I can just make it so that I'm not drawing over it. Those are where your flags are set. This is going to be an extremely important spot to pick out and an easy identifier for what flags are set. I have a 010 as denoted over here, and I know that that is an ACK. So that is your flags. Then you have your 2 bytes for window size coming next, your 0072, and then your checksum, urgent pointer, and then your optional data. Most important thing are the source port, destination port. Sequence number and acknowledgement number is how the packets keep track of what packet is in what order. And you can actually get very granular in packet analysis to figure out what the next sequence number is going to be expected and the next acknowledgement number. To get the next sequence number for what packet is next, you take the current sequence number and add all of the data length of the packet. That would give you your next sequence number for the next packet in the order for how your data is being sent over in packets. And then your acknowledgement number, you would take your current acknowledgement number. They should have raw values in here somewhere. You would take this acknowledgement number and add on the data length as well to give you your next acknowledgement number. So you have raw values in here. We're not going to go that far into depth with TCP headers, but you can calculate the next packet that's supposed to be there by adding up the total data length and your current sequence and acknowledgement numbers that you're given to you. So I'm not going to go that in depth. Yes, there is even more to PCAP analysis, but at a high level, this covers the TCP header. Okay, let's dive into just the flags for another second here, because it's really the most important concept to pick up for the TCP header analysis. We're working with right here, the flags that are set. So we had in the last slide a 0x010 to give us an acknowledgement flag. And I said your flags are always going to be kind of, third row and these three numbers here. So this one, we actually have a value of 0x012, which would give us a SYN ACK flag set. How did we arrive at SYN ACK? These are the values. The values of flags have different hexadecimal notation to them. And the best way to give this of an example is if we think of our TCP three-way handshake. We had a SYN packet go out, a SYN ACK packet come on the way back, and then a final acknowledgement sent back out. Now, the SYN flag, if we look at our values for what we have, has a hexadecimal value of 02. Our acknowledgement flag has a hexadecimal value of 0x10, just like we saw on the previous slide. When you combine these two together, you're going to get a hexadecimal value of 0x12. And that is what we see here for a SYN and an ACK flag set. So at the hexadecimal and even bit layer, you can see the 3 bits are up here for the reserved, not set, and then the remaining 9 bits for what we broke out in the previous slide are given on or off values for the flag being set or not set. So if you had an urge, you would have a value of 0x21. If you had a fin, you would have 0x01. If you had a fin ACK, you would have a fin combined with an ACK, and you would have a 0x11. So you should be able to be familiar with the location that this is going to fall in when you're looking at your hexadecimal notation. You can go to Google and just do the quick values for what flags have what set, and you can also just cheat in Wireshark, and the 0x12 will just tell you it's a SYN ACK packet, but it is important to realize where these flags are coming from. You can write filter notation to also denote what flags you're looking for in hexadecimal, and then all of these packets would be a SYN ACK packet. So a little bit more detail on the flags there. The last header that we're going to discuss, a lot easier to digest, as we discussed TCP, complicated, slower, has all the handshakes, uses flags. UDP, send it and forget it, so it's much simpler of a header compared to TCP, as we would expect. So finding our frames, we have our Ethernet. 86DD is where the Ethernet ends. 86DD means we're going to go into IP version 6. That means the IP version 6 header is going to start here, and then the IP version 6 header is going to end right here, and we are now going into our UDP header. If we didn't know that, going into UDP, I'm looking for 11 in hex, which is right there. So looking at this, we have our source port denoted as the first bit, the first byte, first 2 bytes of FE8F, which gives us the value of the random hide port. So again, this is the client sending this packet. Destination port, the same value that we saw, 01 BB for 443. The length taking up the next 2 bytes, so 00, pick a different color, 0025. 25 in hexadecimal is 37 in decimal. Checksum, the next 2 bytes, 8C1A, and then the rest of this is just all of the data for the actual payload that's coming over of 29 bytes worth of data. So a much easier header to understand is the UDP header. Congratulations on making it through section 2 with the header analysis. I know it's a lot. I did my best to explain it. Hopefully you can watch it again and have the terms and the placement of the bytes become more familiar to you.